Welcome to Power Up, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on power electronics technologies and products featured on powerelectronicsnews.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges, and opportunities for power electronics in markets such as automotive, industrial, and consumer. Here is your host, Editor-in-Chief of Power Electronics News and Embedded.com, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of Power Up. Today we explore the dynamic world of industrial microcontrollers, digital power, smart control, the role of microcontrollers in robotics and server power supplies. Today's episode is brought to you by our sponsor, Infineon. It's a pleasure today to have a special guest, Marijana Vukicevic, Marketing Director for Industrial Microcontroller at Infineon. She is joining us to discuss the evolving role of microcontrollers, MCUs, in high-performance motor control and power conversion applications. As industries shift from analog to digital power systems, MCUs are at the heart of enabling higher efficiency, faster switching, and real-time processing, critical for applications like robotics, industrial automation, and high-density power supplies for data centers. With switching frequencies increasing from 200 kHz to 600 kHz and beyond, the demand for ultra-fast, well-architected microcontrollers is greater than ever. In this episode, we will explore how Infineon's microcontrollers are addressing these challenges, particularly in robotics and AI-powered motor control. We will also dive into the role of GaN-based power systems, the increasing power demands of server racks, and what the future of microcontroller architecture looks like for next-generation embedded systems. Let's talk with Marijana. Hi Marijana, thanks a lot for being here. How is it going?
Good. Thank you, Maurizio, for having me join your Power Up podcast today.
Thank you so much. Where are you located?
I'm located in our Infineon's El Segundo office, which is in Los Angeles County in California.
Good. So today we will talk in terms of digital power, smart control, and the related topics. Before starting, could you start by introducing yourself, telling us more about you, about your role at Infineon, your journey, career in the semiconductor industry?
That's very interesting. Yeah, thank you so much again for inviting me to Power Up, and it's actually very timely and appropriate. I have been in this industry for almost 30 years in power industry from all kinds of different perspectives, and basically anything from design. I did design for more than 10 years, and then I moved to marketing, and I moved to consulting and foundries and from all kinds of different angles, but always on power. And today I'm in the role of the marketing head for Industrial MCUs at Infineon. That is essentially the section of our company which we acquired from Cyprus. So I'm more on the Cyprus side today than I was before. So when I joined Infineon in 2018, I was more on the Infineon side, and at that time we didn't have Cyprus, and today we have it. So, but nevertheless, my role is still in power, regardless of the fact that I'm product marketing for MCUs. What that means is that over the past 3 decades that I watched so far, we have moved from analog controls to digital controls, and I saw the history in front of my eyes shifting from everything being analog to shifting to digital in power conversion and motor control.
Good. So let's stay in this about this focus. So the shift from analog to digital systems that in power electronics is an important trend, especially as you said when we are talking about power supply in this case, but also motor control. This shift enables also more efficient operation, greater scalability, and faster switching, in particular when we are talking about motor control. So which industries or markets have driven this transition? So what are the general benefits to give us an outlook of moving to digital solutions in power management?
So it's a very interesting, I think, journey for power overall over the past several decades. But at the time when I started my career, basically the digital control started at that time, right? So that was like mid-90s. And it started even before, but it was more on a very innovation level. But this was like sometime in the 90s. The digital control started at the level of, let's create products. And in the beginning, those were most of the cases were at the FPGA level. And then the market started I think moving a little bit more toward digital, but there was a very high pushback for digital. Primary reason was that there was a belief that analog was much higher performing than digital for many applications. And one of the applications, the interesting applications, was audio. And I know audio is not necessarily a topic here, but I'm just giving it as an example, right? So in audio specifically, people thought there is no way that audio control should be and could be replaced by digital, right? So from analog to digital. And primary reason for that was, the quality of the signals was never going to be good. And yet, audio was the first one to adopt, one of the first applications to adopt digital. And what are the reasons behind it for the adoption of digital in power electronics overall is, first of all, there is a need for adding new features without footprint increase. In analog, when you add a feature, there is a footprint because you add another transistor, another capacitor, another this, another that, and basically to create a circuit, or to add basically one of the simpler ICs, but you still need to add a circuitry around, so there is definitely increase in the footprint. Another one is that performance of the digital control has achieved in many cases or even surpassed analog performance. So digital was becoming better and better. And then the system flexibility that is possible to achieve with digital is not possible to achieve with analog. Meaning, with analog you have to change everything, the hardware. With digital, you don't have to change the hardware. You still have an MCU with a zillion possibilities of configuration, and you can still do it within the MCU. And then another that you mentioned, another aspect of it was ability to adopt the same or similar solutions fast into different end products. That's basically scalability, right? So the customers needed to scale very fast, very easy throughout their product lines. So that's basically what drove the market to adopt a much faster digital control.
Yeah, so this is a sort of scalability not only from hardware but also from firmware point of view, right?
Correct, absolutely correct.
So let's focus on microcontrollers, so MCU. So these are playing an important role in motor control when we are talking about different applications like robotics, for example, industrial automation. So can you share about how Infineon is meeting the growing demand for high frequency switching? If we are talking about from 200 to 600 kilohertz, for example, and how this would impact the performance in terms of motor control, in terms of how would help close the loop in motor control application, in particular when we are talking, as I said, high frequency scenarios.
Yes, of course. So we have several trends in power electronics today, and but there are quite a few trends that are revolving around moving to higher switching frequency. So in power conversion, moving toward higher switching frequency has to do with increasing of power density, say in the data centers, in the AC/DC type of power supplies where the power supplies need to deliver the higher power and so on. And then second one is also increase of the switching frequency, while this switching frequency in motor control is moving toward the control algorithms or control types that require in some cases higher switching frequency, and in some cases the heavier codes like what we call today FOC or field-oriented control. So we have two trends that are driving us. So the higher switching frequency and basically moving to more complex control mechanisms. So and then in addition to that, right, we also have adoption of the new technologies for the switches, right? So, and why the new technologies for the switches? Because everybody's looking for a better figure of merits for the switches, because in almost all applications there is a demand for increasing the efficiency, right? So consequently, we are dealing with, one way or another, we are dealing with a demand in increasing switching frequencies for all kinds of different reasons: the power density, the GaN switches, the motor control algorithms, and so on and so forth. But all of them are somehow needing the higher switching frequencies. The higher switching frequencies consequently means that the higher the switching frequency, the shorter the time to close the loop. Because in power electronics, we talk about closing the loop constantly. Everything is a feedback, right? So you're taking the signals from the output, you're feeding them back, you're sending them forward, and basically delivering finally again the power in every single cycle. So the higher the switching frequency, the shorter the time for closing the loop. The shorter the time to close the loop, the shorter the time to execute the code. FOC has a really complex code. That means that basically, if you are decreasing the time for that switching frequency, you are decreasing also the time to close the loop and execute the code. And then, in the end, you also have the demand for faster response on the load changes, right? Why? Because of the increased switching frequency and because of the devices and the faster devices that you are nowadays using in your systems. So what that consequently means for the cores is it requires faster cores, in sometimes several cores. And then it also requires optimized architecture for the execution of these closed loops, right? Closed loop algorithms. We had those trends in mind very much when we created our new family of MCUs called pistol control.
So in practice, we have fast core and well-integrated architecture to optimize the performance in this case. Also, so the need for a fast execution, and this is critical.
Exactly. So the architecture is also critical. What it means is that the architecture needs to be in such a way to allow uninterrupted execution of these control loops.
In particular, in algorithm that we are talking about in real time, humanoid robots, for example.
Correct.
Right?
Yes.
So when we are talking about power, efficiency, switching, so I have to mention GaN, gallium nitride. I mean, so as GaN technology becomes more prevalent in high efficiency power systems, so microcontroller would play a role in handling this was switching demands of GaN devices. So how microcontrollers support the fast switching speeds of GaN and help manage the power conversion processes effectively. So what's the benefits of these microcontrollers working with GaN?
Okay, so I think that's a very important question today. GaN is the wide bandgap type of material, and GaN has a different properties than just the traditional MOSFET switches. So some of the properties relate to actually GaN being very fast in responding to the on and off basically requests. So meaning PW, right? So as such a device, you really have to be able to control it in a way to perform to perform up to its abilities, right? So you can't really slow down GaN, nor you should try to basically make out of GaN something else. So you really should support GaN devices throughout your power paths of signals, right? So that means that directly translates to the needs in microcontroller, and we see several benefits in creating such microcontrollers. And some of these characteristics in microcontrollers that need to be contained are actually very fast, very good peripherals. What we call as peripherals in microcontrollers is actually very often the analog part of the microcontrollers or the a part of the microcontrollers that interacts with the outside world. Which means that in this case, that means that ADCs, for example, need to be really high performance, that PWMs have to really have high resolution, and resolution in some cases has to be even in a picoseconds. So that is why, going back to our first topic, that is why finally the digital power, digital control is getting accepted, because these peripherals got over time better and better and better, right? So, and what are the clear benefits of using microcontrollers that can meet the demands of switching GaN and switching frequencies in the system, meaning GaN to switch at much higher frequencies? Is the benefits are very clear for the entire system. You can't take the control outside of the full system solution, nor can you take GaN outside the full system solution. So the benefits are smaller footprint, higher efficiency, and higher power density. Because we can touch a little bit on the power densities as well and what it means, especially in the data centers and AI and so on. For what's really important to know is and I'm going to try to describe it in the less technical way. The more MCU is the real time, the higher the efficiency. What that means is there is no delay between what's really going in response to the real dynamic changes in the system, because if there is a delay, the system may see some discrepancies that will contribute to the loss of the efficiency. So essentially, the more the real time MCU is, the higher the efficiency.
Good. This is a nice point. So I have a question about an application, but just focusing on this real-time algorithm. So you mentioned also the fast execution for high-frequency motor control systems. The need for that fast execution is critical. So what about the architecture, microcontroller architecture, the design of the core as well would influence the ability to execute complex control algorithm in real time? If we think about humanoid, as I mentioned first, humanoid robots powered by AI. So this would be important in terms of real time, in terms of efficiency, as well as automotive autonomous driving in practice.
So humanoids are also special application in many ways. All these applications that we are talking about, they're different in terms of the requirements. Yet there are many similarities. So in terms of the humanoids, when we look at and let's take as an example humanoids so that we don't generalize too much. But in humanoids, you have many points for for example, for the motor control, right? So you have the fingers and you have the arms, you have the elbows, you have all kinds of spots with motor control. What are the most challenging things in humanoids are essentially that basically the spaces are very small. Look at the fingers, for example. The knuckles are very, very small and tiny. So that's one. And the second thing is the fast communication between the central microprocessor and the peripheral units, right? Meaning motor control in the fingers and so on and so forth. So that determines what are the requirements for the MCU and the whole system. So number one, small footprint. That means it's better be actually the small switches. The smaller the switch, and basically to be able to fit in such a small footprint. And also it means that that will require, in order for the whole system to be very small, that will require also the higher switching frequencies. Motor control nowadays is getting more and more complex. And today, in many cases, we are seeing usage of FOC, field-oriented control. That's one of the most complex control algorithms in our power conversion systems. So it's very code heavy, and the higher switching frequency means the smaller periods and the smaller time to close these control loops. And when you have control algorithms that are code heavy, then you really have to execute very fast in order to satisfy such a small and short period of time to close the loop. That means that the cores have to be very fast, the peripherals have to be very fast, and in addition to that, you also have to be able to communicate very fast to the central MPU in the humanoid, right? So for that, you need really fast communication interfaces, and basically some level of differentiation between the protocols and so on and so forth. So we are seeing the trend for EtherCAT, we are seeing the trend for CAN for the communication in humanoids.
Thank you. So talking about another application in server racks, as the power supplies move towards higher switching frequency, what specific challenges arise for microcontroller performance and power management?
So in server racks, Today we have the trend of constant increasing of the power per rack. So we are today somewhere in the range of 30 kilowatts, 25 to 30 kilowatts per rack, but that is moving very fast toward 100 kilowatts per rack and even higher. So without changing in the space, it's not that the space now is tripling and there are basically now the racks are becoming 3 times bigger. No, the space is staying the same. It's just that there is a requirement to deliver more power. So what that means is within the same space, you need to deliver more power, which means much higher power density. In order to achieve higher power density, you have to shrink everything. The only way to shrink everything is to move to higher switching frequencies. So in power conversion, the codes themselves, they're not as intensive, but the switching frequencies are much higher. So in motor control, you have, for example, switching frequencies around 100 kilohertz in humanoids, or maybe 150, but that's the top. In power supplies, we're going to be seeing 500 kilohertz, maybe going toward 1 megahertz, and maybe even above. So that means that the time for closing the loop is really shrinking. Even though the algo is not so heavy, but the time is shrinking so much that basically closing the loop is going to be challenging as well. So for that, we also need very high, very fast cores, very fast peripherals in order to close that loop really fast and meet the demands for the next generation servers in AIs and other server applications.
Great. So thank you. So my last one for you, Marijana. So in conclusion, given the growing demands of robotics server application, as you mentioned, so in the next for the next years, so what advancements in microcontroller design do you foresee in the next 5-10 years, more or less? Or in another way, what features in terms of architectural features should be prioritized in microcontrollers for application like robotics and motor control, not only in terms of architecture, probably also in terms of firmware motor control codes, especially when dealing with higher switching frequencies.
Yeah. We do have several aspects of the whole ecosystem. For us, ecosystem is the full hardware and software and tools ecosystem, and that needs to be in place in order to meet the demands of the market. And the market is moving faster and faster and faster. The customers are going to need more and more and more of our help, right, for the entire ecosystem. So the trends that we are seeing currently in terms of the hardware is for sure faster cores. And we have to start, we are going to be investing into faster and faster cores in order to meet these demands for the higher switching frequencies. There is no doubt about that. We also will need faster peripherals, meaning ADCs, PWMs, high resolution, and so on. We will need faster communication interfaces. Humanoids, the advancement in humanoids over the past several years, 1 or 2 years, is huge. Not to say even within 1 year. The one past year, what we are seeing in the market today is really huge. When you see robots not reacting fast enough, that means the cores are not reacting fast enough and the communication is not in place. Fast communication is not in place. So all that needs to progress further. And the last one maybe, and all of this is also software and hardware related, because, for example, the faster communication, one part is hardware, but the other part is protocols that you put on that hardware. It's the software stacks that you put on that hardware, right? So everything is software and hardware. And then the last one is for sure that maybe it was not so obvious for the past few years, but we are seeing clearly the trend is the security, increased security. Increased security. We didn't touch much on it so far, and maybe that's for some of our other podcast topics. But security for sure is changing in the power supplies, in the data centers. Security is super important in humanoids. Security is super important in industrial automation overall.
Yeah, considering everything is connected, security is important everywhere.
Absolutely. Yep.
Thank you, Marijana. Great conversation. Thanks a lot for sharing these great topics, and keep in touch with Power Up. Thank you.
Thank you so much. Thanks.
This episode of Power Up was brought to you by Infineon. Thank you very much, Infineon, for sponsoring us. If you want to learn more about Infineon solutions we have been talking about today, please check the links on the podcast page at eetimes.com or the Infineon homepage, infineon.com or powerelectronicsnews.com. Thank you.
That brings us to the end of this episode. Stay tuned for more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. Power Up is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio, and the producer is James Eade.